Okay, I keep trying to record this as I'm doing it, and my phone keeps messing up. So I'm just going to explain what I did rather than redo this again. So here's the two tanks, right? We've got the height of the water in tank 1, the flow of the water into tank 1, the flow out of tank 1, the height 2. You guys know all that. The first thing you want to do is represent the problem, right? And we did this in the lecture. He went over it quickly, and maybe you didn't understand what you were doing, and that's okay. But you do want to understand this part of it rather than just kind of passing it on, because it makes sense for everything else that you do. So we described the water changing as a change in volume. The volume of the water is equal to the area of the tank times the height of the water. So area H1, that's where that comes from. That's why V1 is important. Now, to describe that as a function of time, it's the change in volume over the change in time. And if you do the same thing, the area of the tank is a constant. It's not a function of time. The area of the tank is not changing. So now you can describe the water changing as the area times the change in the height over the change in time. Okay, so that's where that comes from, and we'll use this equation later, and you'll see that. And you'll see that you have the same thing for the tank 2. Now, for the flow rate out, FO2, this is the flow rate out of the tank, the first tank. We were given in the lecture, and you could have figured this out yourself. You don't necessarily need the lecture to figure this out, but the height of tank 1 minus the height of tank 2, because if this is high, it's going to add back pressure. And so it's going to actually try and push water back into tank 1. So that's why it's H1 minus H2 divided by the rate of flow that's allowed. So essentially there's some fluid dynamic going on here that allows a certain flow rate. So it's not going to be able to just compensate for regard. I don't know. I think you understand that, though. I'm not going to try and explain it because I don't really understand it, but I know what that number represents, or what that value represents. So then do the same thing. You were given that. Let's also look at the flow rate out of 2, which is given as the height of tank 2 and the resistance value or the flow rate value coming out of this pipe for tank 2, which is going to be part of that formula for the flow rate of T out of tank 2 as a base of time. And then what you may notice, or what may confuse you, is you don't have a formula for the flow rate of coming into the tank, and you don't need one. You know, the whole point of this is to represent this system with different parameters as an input, and this is your input. So every time you see this, it's just going to be F1 of T, because we don't know what F1 is T. That's basically what we're kind of deciding, or we're figuring out how F1 of T affects the heights of the tanks of water. That's the point of this equation. I'm sure you understand that. So let's get to work right away. So we've already shown that the change in volume over the change in time is equal to the area times the change in height over the change in time. But what we didn't necessarily look at is that the flow rate out of tank 2, or we might have already looked at that. I think you guys understand that. Flow rate out, flow rate out. So now let's use this little formula that was given to us, that the change in volume over the change in time can also be considered as the flow rate into the tank minus the flow rate out, because that value will represent the change in volume, the change in height of water. So this is basically where that formula comes from, and we do the same for the other tank. The flow rate in, which is going to be FO for tank 2, the flow rate in to tank 2 minus the flow rate out. So hopefully that makes sense to you guys. And now we're going to move on to how we get to our first formula for part B of 1.2. So we have this formula here. Well, let's substitute the change in volume over the change in time with our equation here, A1, the area times the change in height over the change in time. So that's where this comes from. So we go from this step to this step. Now, moving from this step, we have A1. It's basically we're plugging in values for this formula that we already have. A1, change in height over the change in time is equal to the flow rate in, see where that comes from, minus the flow rate out. And this flow rate out is this formula right here. So now you see where this comes from. Okay? Simplify your equation, and you'll see that the change in height over the change in time plus the height of tank 1 divided by area 1 R12 minus height of 2 divided by area 1 R12 is equal to the flow rate in divided by A1. This should look pretty similar to that. See that? And now, so let me show you a little helpful key on how that kind of transpires, how we get exactly to that point right there. A11, H1 of infinity plus A12. Okay, so if you remember in class, when you do the limit as something approaches infinity, the rate of change is no longer happening. The change in time is at 0 at that point, so to speak. So this value is 0. The height's no longer changing. It's reached its maximum value or its steady state value, so we don't have to worry about it. And we're assuming that the system is stable so that it does actually reach a steady state value and it doesn't keep oscillating infinitely. So this is 0. This is h1 of infinity, so you could write this as h1 of infinity if you'd like. You don't necessarily need to. This is minus h2 of infinity is equal to f1 of infinity. In this problem, they keep calling f1 a constant, which is necessary. So because it's a constant, we don't even have to write t anymore. f1 is a constant value that does not change. So let's just call it f. We know f is not going to change. Whatever value it is, it's just f. It doesn't change with time, so you no longer need the t next to it because it is constant. So from this right here, knowing that this is 0, this right here is your A11. This right here is your A21. And then this is your B1. So you have now step B figured out. Do the same for the second equations for how the change in volume of tank 2, which is up here, change in volume of tank 2 is related to the flow in. So I kind of started doing that down here. You can see A2 change in height over change in time, H1 minus H2, and so all of this right here, this comes from this equation right here. So for change in volume, change in time, you have this. So substitute this right here. For flow out, you have this. So substitute this value for flow out. And for flow out of 2, F2, we already have that formula also. So plug this guy in for there. And so when you're done, you'll get this. And then when you simplify it, you should get this. Change in height over change in time minus 1 over A2 R2, or R12 plus, yeah, you see it all. Make sense? I hope so. So now let's flip it over and get you to the next part of this process. And I'm going to go through it again, get through a few steps, and then I'll record and explain what I did.